Good morning, everyone. I am Avinaya Tripathi. I am a assistant research scientist at Arizona State University, working under my advisor Narayan Ithalath. And I'll be talking about some print filament modifications and print technique alterations that we can do to get enhanced mechanical properties out of the same system. So 3D printing generally, with all things going around, I think most people have been familiarized with it. It's basically the lack of form work, the freedom to create weird kind of shapes, the geometrical freedom, topology optimization, all these things that 3D printing allows us to do. It's gaining a rapid interest for itself. There's like lots of advantage and disadvantage to the system. We'll focus on the advantage, obviously, while trying to kind of mitigate the disadvantages. So at ASU, we have a gantry-based system that's like that has a print capacity of 1 by 8 meter by 1 by 8 meter by around 1 by 7 meter tall. So to start with, like again, when there are different kinds of printers, there are different kinds of nozzle, there are different kinds of print materials that we use. We'll focus on a certain thing that we did, and I'll kind of describe what I did and why I believe, or we believe, that that's going to be advantageous to a general overall system that people do use. So we usually use a circular nozzle. A square nozzle has its property advantage. Circular has its advantage. Like for in case of, like, let's say your filament is not technically linear, when you use a square, there will be a twist in the filament, while circular would not have that effect. Circular will print a particularly similar cross-section filament even at a twist, like let's say if you have to go 90-degree angle, you don't have to stop and start. You can just keep on printing. So those kind of advantages are there. So we usually tend to go with a 20 mm nozzle diameter, circular nozzle diameter. So while printing, those thing of importance that we see is like usually around the places where you have layers and filaments. When I say filaments, it's a print bead. So those kind of connection points, you'll usually see like smaller voids forming. As the layer height goes up, you'll see those voids being significant. At lower heights, they might not be as significant, but you usually see these voids. And we all know that in printed system, these are slightly weaker than usual cast system because of the interfaces that are formed, the interlayer and the interfilament interface. And we believe it's not just because of the formation of interface, it's the alignment of interface we have in the printed system, such that the layer will be in a single continuous line, while the interfilament joints also will be in single continuous lines. So what we try to do is like, how can we remove this? How can we make sure that they are not aligned? So two simple modifications we started with. One is printing a curvilinear shape that I will call a S shape. That has a chord length of around 100 mm and radius of 120 mm. So we use that chord. We alternated the direction of the chord to make a S kind of print. So what it does is like along the horizontal linear direction, print direction, it will remove the alignment of interfilament joints. While for the basically the build-up direction, the interfilaments are still aligned. So to remove that, what we did was like we staggered the prints by half the filament width. You could stagger it like 10%, 20, 30, but for the sake of work over here, we staggered it by just basically 50%. So each kind of like centers on the previous filament center line. So as a short form, I'll be using LC as linear conventional, where you are not staggering it. Linear staggered LS for the staggered ones. For the S shape, basically similar with starting at S. So for this comparison, we use 3 different mixers. The base mixer is a L30 with a cement to sand ratio of 0.5. In cement, it's a 70% cement, 30% limestone, and a water binder ratio of around 0.35. For the basic same base binder, we added 0.328% of steel fiber by volume and 0.28% by volume of basalt fibers in this mixes. And we printed like large like the ones you see here. We then cut out like cube samples and beam specimens out of them and tested them on the beams were tested in D1 direction only. D2 direction, again, there will be an interfilament kind of strength that comes in. So we are more looking at more of a linear filament, where we are looking the strength in pin direction, but we wanted to look at anisotropy also, because the built-up direction will be important in prints, because that's the direction you'll usually have loading in. So we did all three directions, where D1 direction represents the compression or tension along printed direction, D2 will be along the build-up direction, and D3 will be along the width, basically the filament width direction, the layering side direction. So with this, so for the 4-point bend, we obtain the load deflection graph for all the different kinds of prints we have, rather than, most important is like, again, seeing that steel fiber has a ductility provided to the system, while basalt fiber is giving you a higher strength. Those are major observations, but based on flexural strength, rather than seeing the graph, I'll talk to you in terms of flexural strength we are observing. So keep in note that this is the same mixture. When you add steel fiber, yes, there's a steel fiber, but when you don't add it, it's the same mixture. It takes the same amount of time to print the same volume. It's the same print speed. Everything is constant. The filament width, filament layer height, everything is constant. The layer height is at 10 mm and the width is 20 mm. So for the linear conventional, we got around a 2.3 MPa flexural strength. With the same system, when you curved it into an S-shaped, we got around 2.5, 2.6. It's like a 20-30% increase in the flexural strength without having to do any modification to the system at all. It's just the print method, the filament that's being printed is slightly altered from what it was. So just by that simple modification, without having to consume more time or more material or anything else, we are getting a higher strength. So that's significant, important, because why not get higher strength than getting a lower strength from the same system, right? So this filament that I did not show you here is a 3 kind of filament where we did not alter the direction of the code. We discontinued it from start because at the point of joint, what happened is like there's a higher material deposition on the corners, resulting in kind of a non-linear kind of print where you have like a very high material being deposited on the points where the code kind of meet. While you have a alternated course, then you will have the print as a more smoother, same cross-sectional area. So we focused on the S-shape more than the 3-shape, but again, having something similar in the 3-shape also would have helped us significantly in getting the flexural strength. Now that's on the terms of when the filaments are curved. What happens if you stagger it? So just by staggering also, if we see the linear conventional versus linear staggered, just staggering the print itself made it possible to reach the strength similar to the curving of the filament. So that's also advantageous to your system. We'll get around a 20-30% increase for at least this system. A different mix, a different printer might have different percentage gain based on, we'll have to test those to see, but based on our mix and our print system, we got around 20-30% increase with staggering of the layer 2. With the S-shaped and staggering being combined, we got even further increase on the flexural strength. So that's quite significant to see that the same mix could provide us better strength if we just changed our way of printing those elements. With steel fiber, basalt fiber, as I showed before, steel fiber gave us ductility. Basalt fiber did not provide us ductility because basalt fibers are more brittle. But basalt fiber, as the diameters were so smaller than steel fiber. Steel fiber was 0.2 mm diameter. Basalt fibers were in the range of 0.06 mm diameter. So there were like near 13 filament equivalent to one steel fiber. So when steel fiber breaks, most probably it caused the fiber to completely lose its load capacity at a point, while basalt fibers kind of prevented the certain kind of breakings. And we see like with basalt fibers, we even got a slightly higher increase, though ductility is a question that comes into picture, but as a peak load capacity, as a flexural strength, we saw that basalt fiber provided higher strength. The thing that we see now, another significance is doing a linear versus S for a non-fiber system. S did help you to gain more strength. But when you incorporate fiber, now comes a question of fiber alignment. Because for our S, because as I said, we took the beam span length along the print direction. Now the S does not align along the length direction except 2 points. So most of the fibers are not aligned along the direction of beam. While for the linear print, the fibers are aligned along the length of the beam. So you get more fiber output out of a linear print rather than the S print. Now it becomes a question of like, do you want that fiber output out or not? Like we would technically want it, right? So for those, We did the AIC, we saw like all strength profiles and stuff to see like how, if is it giving us better response in the sense of we can see like the cracking at least in the linear system is at lower strengths compared to a S kind of or a 3 kind of shape where you are able to kind of reach higher strength. Now this TIC is on a surface, right? So the surface does not have the interfilament joints that are coming in between. So it basically shows that there's no strength concentration inside the beam that's initiating the failure, that it's allowing the filament to reach higher strengths to give more load carrying capacities during the failure time. With steel fiber, we saw higher strength at after peak loads, giving us ductility. Basalt fiber did not do so. So for this system now, you did gain flexural strength, but what about compressive strength? Did you gain higher compressive strength, or did you remove anisotropy? To see that, we did like 3-directional test as I described before. What we observed is like in this system, the build-up direction was significantly weaker than the other 2 direction. Again, this the thing that comes into picture is again the interfilament joints. We have papers where we do like just single filament prints, where we have the cubes. Like here we have like 3 filaments side by side in the cube. So we do see that interfilament effect. We do not do that. Like let's say if we print a 60 mm wide bead and just use 1 filament, we will not see the interfilament effects. So interfilament effects are significant in these systems. We have to make sure that we reduce the interfilament defects and kind of reduce the detrimental effect of those interfilaments. So what can we do to further increase it? Like how can we remove the anisotropy? Can we do something to try to get similar strength in 3 directions? Because we did get a higher flexural strength. Why not try to get compressive strength as higher? Because if you print a wall system, this direction, the direction 2 is the system, you will press the wall on. Like you want that direction 2 to be higher rather than 1 and 3 in a wall system where it's a load carrying member. So what we did next was to use the same system, the linear staggered and S staggered. Now, instead of doing a staggered system, what we did was like we rotated the each layers. We now are making sure that the interfilament does not remain in the perpendicular line at all. We made the first layer be the same, but each layer we rotated it by 18 degrees such that when we come to the top of the slab with 6 layers, we are in a 90-degree angle rather than at 0 degree. Now, what does this give us? So when we see compressive strength based on like the first is a linear staggered versus the linear with 18-degree angle, the S staggered and S with 18-degree angle. You don't see that much of a difference in 1 and 3 direction, but if we see the direction 2 for this, we can see that with direction 2 we get significant increase in the compressive strength also now. So kind of showing that now we get similar strength in direction 2 and we are reducing the anisotropy also. Now this is more advantageous. Maybe doing the angle system is good. But as we saw before, the angled fibers, fiber angling to the length of the beam deteriorated our strength, right? So does it happen here? The first layer is at 0 degrees. So the layer that's in the tensile response, the maximum tensile response still is aligned along the length of the beam. It's just the above layers that are slightly angled to from the length of the beam, right? So what's the effect of that? So to see that, we tested flexure for these samples too. So what we see is like for the linear one, because every layer has the fibers oriented such that they are in the length direction, we did see a decrease in the flexural strength with the linear 18 because now your fibers in the upper layers are slightly the angles are slightly not exactly in the length of the beam. They are oriented at an angle to the length of the beam. So we did see that. But with S, we did not see as much of a significant difference. We are seeing similar kind of strength with S staggered and S18, meaning like when you rotate it 18 degree also, you are seeing similar kind of responses. So maybe a combination of printing a S filament while changing the layer orientation by 18 degree will give you higher flexural strength, will remove your anisotropy in the system. So basically it's win-win situation in everything, right? So maybe that's the way to go. Maybe those are the modifications we should be looking at. So with that, I'd like to conclude my presentation by acknowledging the funding agency, NSF, US Department of Energy, AxelNet, and I'd like to acknowledge my advisor, Narayan Neithalat, and my senior, Suraj Egonayar.